So, very pleased to welcome Sucharit. I hope I've pronounced that correctly. Who's going to talk about mine's gone blank. Khovanov homotopy theory. Is that correct?
Sure.
Okay.
Yeah. Thanks for inviting me. So yeah, great. So yeah. So let me. Let me try. This is like I'm still new at this, virtual things. But so so what I'll do is I'll do it the way I've been teaching, which is like on this OneNote notebook. Okay. So I tried doing slides, but it didn't work as well. So okay. So I'll try to keep it as close to a Blackboard experience as possible. So that'll be the OneNote thing for now. But please interrupt me, okay, if you have any questions, because it's not in a room. It's hard to see videos. It's hard to read people's reactions. So please interrupt me and ask questions, okay? I won't be able to follow the chat because some people are very good. They also follow chat, but I won't be able to do it. So, if you have any questions, just interrupt and speak out. Okay. So with that being said, thanks again for inviting me, and let's go. Let's see how it goes. So, okay. So almost everything that I'll talk about today, it's joined with my long-term collaborator, Robert Lipschitz. And a lot of it is also with Tyler Lawson. Okay, so I must mention that at the very beginning. Okay, so so let me start with a little bit of the history of Khovanov homotopy types. Khovanov homotopy type. Okay, sorry, that's my handwriting on a vertical screen, but sorry, but hopefully you can read this. Okay, so so a little bit of the history. So the first paper, we joined with Robert, so me and Robert, so we constructed a Khovanov homotopy type. And then I should mention this, so that means that we constructed a space whose homology is Khovanov homology. Okay? So the way the theory works is that if I have a link in S3, long time ago, like right around when I was born, Jones constructed the Jones polynomial. I guess it's called VL. So it's a Jones polynomial. And then in 2000, Khovanov constructed a Khovanov homology. So of the link. So this is the first one is a polynomial. The next one is a homology. And how do you get a polynomial for? So this is a generalization. So you take the Euler characteristic and you get the polynomial. So the homology is actually has an extra grading. So it has the homological grading and an extra grading called the quantum grading. So if you take the Euler characteristic, you still have a polynomial left, and that's the Jones polynomials. And that was a generalization. That's like a big breakthrough. And then, so what we tried to do is Lipschitz Sarkar. Oh, I should have put the S here. Sorry. Is what we did is we tried to construct a space. We just called it X of L. So it's just a space, or rather a homotopy type. So the homotopy type of the space, the stable homotopy type of the space is an invariant. And then the way you get the homology is just by taking the ordinary homology. If you just take ordinary, I guess, reduced homology, you get Khovanov homology back. So instead of a homology group, you now have a space. So that's our generalization, that's our construction. And then, but now what's the advantage of having a space instead of a homology group? Actually, let me just talk about the previous advantage. What's the advantage of having a group instead of a polynomial? So first of all, the polynomial is already pretty great. I mean, the polynomial, the Jones polynomial historically has been very useful for solving problems that have been open for 100 years. Okay, so this is the history. I'll just say it out instead of writing it down. For instance, you could use Jones polynomial to prove properties of alternating knots. Okay, so there were the state conjectures which were open for more than 100 years, and they could almost 100 years, and immediately with the Jones polynomial one could prove them. Okay, so as Kaufman did and others. Okay, so this is very useful for proving properties about alternating knots. But it still is a polynomial. So this lifting it to a homology group is actually the main thing is that it actually becomes functorial. So Khovanov homology is functorial. So what do I mean by that? Is that if I have S3, and if I have some link inside S3, let's call it L0, and if I have S3 again and some other link, I'll just write L1. So here is L0, here is L1. And now if I have a cobordism in S3 times the interval, from this link to that link, I mean, it could have genus, it could be anything. If I have a cobordism, let's call it F, from this link to that link, well, in terms of Jones polynomial, there is no relation because polynomials don't have morphisms. But in terms of Khovanov homology, this surface will induce a map. Let's call it KH of F, from KH of L0 to KH of L1. So anytime you have a cobordism between links, you have a map between their corresponding Khovanov homologies. So this is actually strictly more information, and so this gives you more information. It gives you more structure. So this gives you more information, more structure, and so on. Okay, so I guess I am like also talking about applications at this point. So applications, like these are just some of the applications. Like you could do. Yeah. Good. So what was the question?
I'm sorry, I think I was just starting out. Excuse me.
Oh, it's okay. Sorry. Yeah, go ahead. So, but anyways, like, so here are some applications. Like, so the Jones polynomial the Jones polynomial can be used to prove Tate conjectures about the minimum crossing numbers of alternating knots. I'll just mention this. This is like Kaufman and Morris. Okay, so this you can like use Jones polynomial to prove Tate conjectures. Let me just write Kaufman. Others. And then for Khovanov homology, it's strictly more information. So you can like use Khovanov homology to prove Milnor conjecture. So prove the Milnor conjecture about a 4-ball genus of torus knots. So the 4-ball genus of a PQ torus knot happens to be exactly P minus 1 times Q minus 1 by 2. And this was proved using Khovanov homology by Rasmussen, Jack Rasmussen. I mean, it was proved earlier by Kronheimer and Rovka. I mean, so it wasn't a conjecture when he proved it. It was earlier by Kronheimer and Rovka, but not using Khovanov homology, using gauge theory. Okay, so these are some applications. And now what we are doing is like, so, and that really uses this functorial part. I mean, this proof by Rasmussen really uses the fact that anytime you have a cobordism, you have an induced map on Khovanov homology. And then, so what we are trying to do is like, we're trying to construct a space whose homotopy type is an invariant, and his homology is going to be Khovanov homology, and having a space gives you strictly more information. So if you get spaces, like, so with a space you get like better bounds, so it's more information. This is like strictly more information. It's still functorial. This is still functorial. That means cobordisms still induce maps. Okay, and has more information. Let me just, so gives you more information about 4-ball genus and so on. Okay, so there's like, I can give you some examples of like, you can compute 4-ball genus of more knots using this. Strictly more information, but in any case, it's like a generalization of an existing theory. So let me mention a few of the things people have been working on, or what we have been working on since coming up with this space, and so this will be also like a good. So what we did is like around the same time, so a little bit of the history. Around the same time we were constructing this space, Krish, they were also constructing a space, so they also came up with a different construction. There is a different construction of the same space. So that's what with Tyler Lawson. So we proved that they are the same. So we proved that they are the same. They are the same. It's actually giving the same construction. And in the process, like, so we also like computed, so I'll just like mention a few things. So what's the good thing of having a stable homotopy type? So stable homotopy types have extra operations, like has extra structures. Let me give one example. Like for example, the Steenrod squares, SQIs. Okay, so if it's just stable, we don't get the actual homotopy type. We only get the stable homotopy type. The stable homotopy type is a link invariant, and so cup product is not a thing on stable homotopy types, but Steenrod squares are. So like there are like Steenrod squares. There are many other things, but Steenrod squares is one example. So in addition to homology, you have these extra operations called Steenrod squares, and we could write down formulas. So we wrote down formulas, we computed them, and so on. And then we could show using the formulas that there are knots with with the same Khovanov homology but different stable homotopy types. So this is a strictly stronger invariant. So I guess I'll say so. Cotton seed carried out computations and showed that the Khovanov homotopy type is strictly stronger than Khovanov homology. And then how can you distinguish them? Well, they have the same homology, but then they have different Steenrod squares. So they have different, I guess, SQ2. So he computed SQ2 and he showed that they are different. Okay, and then so this is just still about the Khovanov homotopy type, but then theory has been extensions. So there have been extensions. So let me mention a few. So I guess separately, independently, there is Loeb, Orson, Schutz, yes. Loeb, Orson, Schutz, and Mike Willis, and they extended the theory. So they constructed. So they extended to colored Khovanov homotopy type. So there is a generalization of Khovanov homology for colored links, where the different link components are colored by different representations of SL2. And so there is a definition of colored Jones polynomial. There is an extension of colored Khovanov homology, and so they extended to colored Khovanov homotopy types as well. Let me highlight Mike Willis. He's a postdoc. He's one of my postdocs. He's on the job market this year. So if you're if you're looking for someone, there is one. Okay, so anyways, but some other extensions. So there is also like a generalization of Khovanov homology to there is something called odd Khovanov homology, and so there is like an odd Khovanov homotopy type as well. So this is like we did this with Christopher Scaduto, Matt Stoffrigan, and myself. So we generalize this to odd Khovanov homotopy type. So in some cases there is like an immediate generalization. In some cases you need some more ideas to produce this space, and in some cases you get stuck. Okay, so I'm only describing the ones where we don't get stuck. But so not always. So there are many different generalizations of Khovanov homology, and not all of them has an immediate generalization to Khovanov homotopy type. So in many cases we do get stuck. Okay, so those we are not listing. I'm not listing. There is also sort of a generalization. So this is actually an interesting thing. So periodic links. So it's a link with some sort of a symmetry. Okay, so like or periodic knots or periodic links. So let's give an example. So here is like the trefoil, and this has a Z mod 3 symmetry. I can rotate by 120 degrees. So there are these things called periodic links, and so that means I should expect a group action like Z mod 3 to act on all the relevant theories, and so the Z mod 3 group does act on Khovanov homology, but a group action on just a group on homology doesn't give you so much information. But if we could construct a group action on the space, this gives you a huge amount of information. And so what they did is but from the construction, it's not immediate that you can get a group action, but that's precisely what Stoffrigan and Zhang did. So they constructed a group action on Khovanov homotopy type, and this gives you a lot of information. And this gives you a lot of information even at the level of Jones polynomial. So it tells you things about the Jones polynomial of periodic links, which we didn't already know. So this was also later done by, let me cite them, Politarchik, Silvero, and Borojic. Sorry. So and Borojic. Okay, so it was done by them as well. So anyway, so there's like maybe I'll let me mention a couple of more results that people have been doing. So also, by the way, I mentioned that we can get formulas for Steenrod squares. So Moran came up with these formulas independently, or a different set of formulas, I think. So he came up with some other formulas for Steenrod squares and for all the higher Steenrod squares. So there is like some formulas there, and once again for periodic links. There is something called quantum annular Khovanov homology. So there is something now called quantum annular Khovanov homotopy type, which is a generalization of Khovanov homology, but it's for links like this. It's for periodic links like this, and this was like done by Meshet, Slava Krushkal, and Mike Willis. Again, Willis is my postdoc. He's on the job market this year. Anyway, so you can also get that, and they also constructed an SL2 action on the space. So there was already an SL2 action. I'm sorry, USL2 action, whatever. It's like there was already an SL2 action on the Khovanov homology, and they constructed an universal enveloping SL2 action on the Khovanov homotopy type. Kind of like that. So that's like a brief history of where the theory is going. It's fairly active. People are constructing different generalization. So Khovanov homology has sort of branched into different things. It's a very rich theory. There are lots and lots of generalizations of Khovanov homology into different, with different techniques actually. And then we are trying to catch up. So we are trying to construct like stable homotopy lifts of all of them. And here are some. So here are some stable homotopy lifts of some of these things. So, and I guess I can mention our things as well. So what we have been doing is like, so with Lawson, Lipschitz, and myself, we are also constructing like homotopy lifts, stable homotopy lifts for tangles. So tangles are links with sort of like boundary, you know. So here is a sort of a tangle. Here is a tangle. It's a link with some boundary, and then there is already a Khovanov type theory for tangles, and we are trying to lift it to a Khovanov type theory. I mean, we lifted it to a Khovanov type theory for like Khovanov homotopy type thing for tangles as well. So tangles, and okay, so, and we are also working on cobordisms, right? So and this is like another example why homotopy types are sort of much more interesting. So let me mention like why cobordisms are more interesting. So again, let me draw the same picture, that let's say I have a link L0, I have a link L1, and let's say I have a sort of a cobordism F from L0 to L1. So then I get a map, like I said, from Khovanov homology of L0 to Khovanov homology of L1. Maybe I should write the map here. Sorry. So Khovanov, so I get a map like this, but not just that. So we also get these cobordism maps. So this is a very recent work. We are yet to sort of put it on the archive. So, but we also get a map on the level of spaces. So there is a well-defined map at the level of spaces. So there is a well-defined map at the level of spaces, so that if you take homology, so this vertical arrow is homology. If you take homology, you get the induced map there, okay? So if you apply the homology functor, you have the induced map on Khovanov homology level. But a map of spaces is actually strictly more information than a map of homology groups. So this is like, I really sort of want to stress this. This is strictly more information. So we get examples. So we find, so we have an example of an actual cobordism where the map on Khovanov homology actually has to be 0 for grading reasons. So what do I mean by that? Like, so for instance, like, so it kind of looks like this, that at the level of Khovanov homology, there is a Z in, let's say, grading n+1. So this is a Z in grading n+1. And then there is a Z in grading n. So if I have a Z in two different gradings, then I cannot have a map between them because the map is grading preserving. So this map actually has to be 0. There is no option. Okay, but there are non-grading preserving maps between spaces. So if the homology of a space is just Z, then the space is most probably Sn plus 1. Okay, so the space is Sn plus 1. I mean, the reduced homology is just Z. So at the level of spaces, it's just Sn plus 1, and this space is Sn. But there are interesting maps from Sn plus 1 to Sn, namely the Hoff map. Like, I guess it's written by eta. Okay, and then we get an example of a cobordism where the map at the level of homology is 0 just for grading reasons, but the map at the level of homotopy type is interesting. Namely, it's a Hoff map from the Sn plus 1 to Sn. Okay, so this is actually exciting, right? So you get, so in general, like, I don't have to stress this, like homotopy type contains more information than homology, but particularly more so when you're considering maps. When you're considering maps, it's like usually much more information than homology. Okay, so that's like a brief history of applications and like where the theory is going. And now let me tell you how the construction works. So I'll pause for a little bit. Any questions? Or
Sorry?
yeah.
Yeah. Do you have a theory for virtual knots and links?
I don't actually. So sorry, that's a reasonable. Sorry, yeah, that's right. So like there are like Khovanov homology type things for virtual knots and links, and just we don't.
Yeah.
Do we have
excuse me.
Yeah. Go ahead.
I and A.G. Ogassa and Igor Nikonov are working on these kind of constructions for virtual links, and we have some papers on the archive. The work is in process.
Sorry. So yeah. So let me cite Kaufman and sorry, who else?
Oh, sorry, Ogassa.
Ogasa and
Nikonov.
Konof.
Yeah. Mm-hmm.
Okay, great. Yeah, sorry. Yeah, so great. Yeah, so there are other sort of theories developing, and of course, my apologies. I tried to like mention as many people as I could, but I surely have missed out other people because there are a lot of people working on this. So yeah, so if I missed out anybody, my apologies. But that's so yeah. So that okay, great. So. An interesting thing is like, so there are like things which we couldn't generalize. So I should mention this because that's actually the more interesting thing, right? So these are things which are already done. Okay, so the things which are not done is more interesting. So we are stuck. So this is actually important. Stuck. I'll write it in red. So there is like a generalization of Khovanov homology called Lie perturbation or Barnerton perturbation. So this Lie or Barnerton perturbation. So they constructed sort of a perturbation of Khovanov homology. And this is actually a very rich theory, and we cannot construct a similar thing at the level of spaces. We are just stuck, okay? So we need new ideas for this. I mean, like you try the obvious generalization or maybe it's not so obvious generalization, but none of them works. And the other one is like SLN or the Humphrey homology. So there is like an SLN polynomials, and there is famously the Humphrey polynomial, and they also have these homology things. So but what about the Humphrey or the Hom-flipped theory? So there is already a Hom-flipped polynomial and a Hom-flipped homology group, but what about a Hom-flipped homotopy type? Okay, so we are stuck in these two things. I just wanted to mention that. Okay, so these are good problems. Okay, I mean, okay, great. So
I have a silly question. What do you mean exactly by a stable homotopy type?
Sorry, I should have like mentioned this. Stable homotopy type. So what is X of L? So X of L, like, so we have a link in S3, and we are constructing X of L. And what we do is like the way we construct it is we construct it as a CW complex. So this is a CW complex. I mean, finite CW complex. There is nothing infinite here. It's finitely many cells, everything. It's a finite CW complex. But this construction depends on choices. This depends on choices. Mostly a choice of a link diagram. Like, so for example, like a choice of a diagram. Okay, so and some other choices as well. But anyways, like you construct a finite CW complex. Now you might say that what if I make different choices? So I could like choose different choices. But like, okay, why don't I write a sort of the choices? So it C for choices. Okay, C for choices. So now I take the same link, but I choose a different set of choices, and I get a different CW complex. So I don't get the same thing actually. So what do I mean it's an invariant? I want it to be an invariant. So I want this space and that space to be the same. And the only thing we can get is like, so we cannot expect the CW complexes to be the same, but the one thing we can hope for is that they're homotopic. They're homotopy equivalent. They're homotopy equivalent, and we don't get that, but we get that they're stably homotopy equivalent. So XLC and XLC prime are stably homotopy equivalent that spaces. That means that if I suspend it enough times, if I suspend it n times, and if I suspend this one n times, then they are homotopy equivalent. Then they are homotopy equivalent spaces for some n sufficiently large. Good? Is that okay? Yeah. So yes. Yeah. So yeah. So stable homotopy type is like, that's what we mean. It's like the equivalence class under this stable homotopy equivalence. So that's what we get. Now this is enough to, by the way, recover homology. Like this is enough to recover homology, but it actually gives you more information than just homology. So that's what I said. Like it also gives you like Steenrod squares. So like Steenrod squares is also an invariant under this equivalence. Cup products are not. Yeah.
Are you going to give us some indication of how to construct this space?
That's right. Yeah. So that's my next goal. Okay. So like let's start. Okay. So now how to construct. So that's the rest of the talk actually. So here is like a construction overview. Okay. So I'll tell you how the Khovanov homology is constructed, and I'll like indicate how we generalize this. So this is how typically the Khovanov homology is constructed. So we start with the link diagram. We start with the diagram, and I'll choose a very simple diagram. I'll choose this two crossing diagram of the unlink. Okay, this is just for some illustration, right? So this is a diagram of the unlink actually. Okay, so then what you do is like you number the crossings. So let's say I number it 1, 2. Okay, and then this is this Kaufman's cube of resolution. So you apply the Kaufman cube of resolutions. What I mean by that is that each crossing can be resolved in two ways, which I guess Kaufman calls 0 and A and B, but we call 0 and 1. So each crossing can be resolved locally by the 1 resolution or the 0 resolution like this. So both the crossings together can be resolved in a 0, 1 to the n possible ways. So there is a 0, 1 to the n resolutions, total resolutions. N is the number of crossings. So this has n crossings. So that's the total number of resolutions. So let me show it. So here is our cube. So 0, 0, 0, 1, 1, 0, and 1, 1. We'll draw the cube sideways. It's a two-dimensional cube. And so 0, 0 means you resolve both of them by the 0 resolution. So it looks like this. So I am resolving this crossing by the 0 resolution, but I'm also resolving this crossing by the 0 resolution. Okay, now 0, 1 means that you still resolve the first crossing by the 0 resolution, but you resolve the second crossing by the 1 resolution. So in other words, you change the second crossing. Similarly, 1, 0 means that you resolve the first crossing by the 1 resolution, but you keep the second crossing still by the 0 resolution. And 1, 1 means that you resolve both of them by the 1 resolution. So you're changing one resolution at a time. So you have this sort of a cube of all possible ways to resolve the crossings, like get rid of all the crossings. So you have a cube of resolution, and this is essentially due to Kaufman. So you have this cube of resolution. Now what does Khovanov do? Well, Khovanov applies some, so what Khovanov does is Khovanov applies a TQFT to this. So Khovanov applies a TQFT to it. So I'll explain what that means. So he considers all possible ways of labeling the circles. So I have a bunch of circles over the cube, right? I have a bunch of circles over the cube. He considers all possible ways of labeling these circles by 1s and x's. That's his name, okay? So like label these circles by 1 and x's. So let me show you, and then you'll like sort of, it's much easier if I do it out. So here there's only one circle. So there are two possible labels. I can label that circle 1 or x. Now here there are two circles. So I can label this one 1 and this one 1, or I can label this one X and this one 1, and so on. So there are 4 possible labels of these 2 circles by 1s and X's. So I'm going to indicate that by 1 tensor 1, which means I'm labeling both of them with 1. 1 tensor X, I'm labeling the first one, the left one with 1. I'm labeling the left one with 1 and the right one with X. Similarly, X tensor 1, this is a different label, or X tensor X. So there are 4 possible labels of those 2 circles. Similarly, there are 4 possible labels of these 2 circles. I'll still do it. 1 tensor 1, 1 tensor X, X tensor 1, X tensor X. And finally, over the last vertex of the cube, I just have 1 circle. So there is 2 possible ways of labeling that circle, which I'll denote 1 and X. So this is all possible ways of labeling the circles over each vertex. Okay. Now what Khovanov does is Khovanov says, oh, consider the free abelian group generated by these 2 guys. So this is actually a Z2. And he takes the free abelian group generated by these 4 guys. So that's a Z4. The free abelian group generated by these 4 guys, also a Z4. And the free abelian group generated by these 2 guys, also a Z2. And Khovanov is trying to construct this thing. So what Khovanov is trying to do is like he's trying to construct a sort of a cube of abelian groups. A cube of abelian groups. And maps. Of course, commuting maps. Okay. So he's almost there. He just defined the groups at the level of vertices. So again, remember, these are cube 0, 1. These are cube, and he just defined what the groups have to be at the vertices. So it's Z2, Z4, Z4, and Z2. So he just he hasn't done the maps yet. I'll take out the maps. He hasn't defined the maps yet, but he just defined the groups. So these are the groups you associate to the different vertices. Okay, now he's going to tell you what the maps are. Okay, let me choose a different color. Okay, so now as you travel along the edges, so look at any edge. So there are 2 possible things that can happen. So one thing is that, so you can merge. So here you are taking 2 circles and you are merging them to form a single circle. So as you travel along an edge, you might be merging circles. Well, if you do, you just multiply. So if these 2 circles are both 1, if these are both 1, you just multiply that to become 1. So 1 tensor 1 goes to 1. And similarly, if one of them is 1 and one of them is X, 1 tensor 1 and X tensor X, they both map to X. And what about X tensor X? Well, that just goes to 0. X tensor X goes to 0. So if you ever merge, you just multiply with X squared equals 0. So so this is also a merge. So this is also a merge. So these 2 circles are merging to form 1 circle. So you're still multiplying. 1 tensor 1 goes to 1, 1 tensor X, and X tensor 1 goes to X, and X tensor X goes to 0. Okay. Now the other thing that you could be doing is you could be splitting. So these 2 things are, these 2 edges are split. Like as you travel along an edge, 1 circle could split to become 2 circles. That can happen as well. So what you do when you're splitting is you just take the dual of this map. So whatever map you defined here, you just kind of sort of reverse it. So this is the way it's defined. So X, like this is the definition, but it's kind of like dual of the previous one. So X splits into X tensor X. So if a circle was labeled X, it just splits into 2 circles. They're both labeled X. Similarly here, so X splits into X tensor X, and 1 splits into 1 tensor 1 plus X tensor X. So I'll denote it like that. So 1 just maps to 1 tensor X plus X tensor 1. There and there. So that's how this map is. So those are the maps, and you can check. So now he has defined the maps for you. He has defined them, and the labelings of circles which are not involved in the splits and merge, they are unchanged. So the far away circles, the passive circles, the circles that are not interacting, their labels remain unchanged. That's basically the definition, and you can check that this actually commutes. Like this is a commuting cube. Like every single face commutes. All faces commute. It's not a hard check, but it is a check. All faces commute. Okay, I guess you can check that this face commutes. Like if I start here and go here, I will get the same map. And that map will be this 1 maps to twice of this x. That will be the map both ways. Okay, so now he gives you, so he takes this Kaufman cube of resolution, he applies this Khovanov TQFT, and he gets a cube of abelian groups, some sort of a cube of abelian groups like this. And now once you get a commuting cube of abelian groups, you can get, so let me give names to these maps. I don't really need the names too many times, so let's just give F, G, H, and I as the main names of maps. So once I get a cube of abelian groups, what I can do is like I just take mapping cones, like iterated mapping cones. You just you iterate this mapping cone operation. So if I have a map between abelian groups, their mapping cone is a chain complex. So in general, if I have a map between chain complexes, there is a mapping cone, which is also a chain complex, and abelian groups are themselves chain complexes with zero differential. So if I have a map between abelian groups, I can take mapping cones, and I will immediately get chain complexes. So I take this, so I do it in like steps. I take this mapping cone and this mapping cone, so I get two chain complexes, and these maps induce a map between those chain complexes, and then I take a mapping cone of that. Okay, so what I do is like I take cone of F and cone of I. So I take the mapping cone of this guy and this guy. These are now chain complexes. These are no longer abelian groups. These are now chain complexes. And there's an induced map between them, which is given by these maps H and G. These maps H and G give you a map between them. Let's call it H plus G. There's an induced map between them, and you take the mapping cone of that. You take the mapping cone of that guy. So you take mapping cones like in each direction of the cube, just and iterate the operation. You do it, and you end up with a single chain complex. And if you take the homology of that, you take homology, you end up with the Khovanov homology. So that's the complete definition of Khovanov homology. Actually, I did not lie. The only thing I skipped is I didn't tell you what the gradings are. So I told you that Khovanov homology has also extra gradings, like has two gradings. So there are gradings. There exist like gradings. And I didn't tell you what the gradings are because it's just a talk. Okay, but there are gradings which I hid from this entire picture. So that's the Khovanov homology of a link. Again, let me pause quickly. Any questions? Okay, so maybe you have seen this before, or in that case, this is like sort of boring, and maybe you haven't, in which case maybe this is too fast, but it's either way. So this is kind of
something. It is not boring.
It's not boring. Okay, then okay, I stand corrected. Great. So but anyway, but it's a very fancy construction. Okay, and then of course, like the thing I was mentioning, that this chain complex clearly depends on the diagram. It's a very diagram dependent thing. If there is no geometry sort of involved, like you take this thing and it's very combinatorial. You take a diagram and you do this combinatorics. You take this entire cube of resolutions, which is very combinatorial, and you do this, you define these groups, and you define these maps, and it turns out to be a chain complex, and you take its homology. And so it's a very combinatorial thing, and it turns out to be a link invariant. It turns out to be independent of the choice of diagram. Okay, you just check that it's invariant under Reiter-Meister moves. It's independent, and it turns out to give you deep information about four-ball genus of torus knots. So it's sort of magical. Okay, I mean I think it's fairly magical that how this is happening, but again, if you like combinatorics, this is like it's very exciting. If you like combinatorics or topology, this is very exciting. I think that it's like just coming from this entirely combinatorial thing. There is like unlike Alexander polynomial, like this is in sharp contrast with Alexander polynomial, because Alexander polynomials are very geometric. You take the the z-sheeted like abelian cover, and you take the fundamental group there. I mean, you do something very topological and you get a polynomial. Here you do something very combinatorial, starting from a diagram, and you still get like a homology theory, and it still carries geometric information. Okay, so now let me keep going. So how can we extend this to a space? So we try to like just repeat this construction at the space level. So extend to the Khovanov like two spaces. extend this to spaces. So you start off exactly as before. So you take this cube of resolutions. So what we have to do is like, so maybe, you know, it's better if I it's better if I just write things in terms of functors. So like a little bit of notation, but it's not serious category theory. So here is a category, we call it the category 2. 2 is the category which has 2 objects. So it has 2 objects which are 0 and 1 and a single morphism from 0 to 1. Okay, of course there are identity morphisms as well. There is identity morphism, there is identity morphism, and a single non-identity morphism from 0 to 1. So that's a category. It's a very simple category. And then you have the category 2 to the n. 2 to the n is like you just take this 2 times 2 times, you take the Cartesian product of the category with itself n times. So like, you know, let me just show you 2 squared. So 2 squared has 4 objects. There is 0, 0, 1, 0, 0, 1. Yeah, and anyways, I don't know. So 0, 1, 1, 0, and 1, 1. So it has, am I writing it like that? Yeah, 0, 1. Okay, great, that's fine. And so it has these 4 objects, and it has like 5 non-identity morphisms. I have this morphism, that morphism. So of course there are identity morphisms. I am not drawing the identity morphisms. And I can also compose morphisms. I can compose this way or I can compose that way, and it's the same morphism. I can go this way or that way, and that's a not single composition. So it's a category with 4 objects and 5 non-identity morphisms. Looks like this. So what Khovanov did, so I just set it out in words that he constructed a cube shaped, he constructed a cube of abelian groups. So a cube of abelian groups is nothing other than, it's just a functor. This is another word of, it's a functor from this category 2 to the n to the category of abelian groups. Okay, so that's exactly what we had. Like, because we had this like Z2, we had Z4, we had Z2, and we had Z4. So those are the 4 groups. And I also had these maps. And I knew that the square commuted. I knew that the face commuted, so I could compose them. And composing that way is same as composing this way, which is the long arrow. Okay, so because it commuted, I could construct this functor. So a functor like this is same as a cube of abelian groups where every face commutes. So that's what Khovanov had. So he had this, and then from there you can take these mapping cones, and you can get the Khovanov chain complex. They get the Khovanov chain complex. So once you have a cube, it's just like you get a Khovanov chain complex for free. Okay. Now, if I want to lift it to a space, so lift to space just literally means this, that I have a cube of abelian groups. This is by Khovanov, and I want to lift it to the category of topological spaces. So I want to construct this lift. So that means I would get a cube of spaces which also commutes. So that's what I want. I want a cube of spaces. I want like a space x00, x01, x10, and x11. I want like these are now spaces. I want a cube of spaces so that it commutes. So that if I compose this way and if I compose the other way, I get the same answer. So I want a cube of spaces. And so that if I take homology, I get the original Khovanov cube back. So that's what I want. And if I can do that, I get a CW complex by doing exactly the same process. Like namely, if I already have a cube worth of spaces like that, I can do exactly the same thing. I can take iterated mapping cones. So I'll take mapping cone first along this direction. So I'll get some CW complexes, and then mapping cone of spaces is also a space, and then I'll take mapping cone in the other direction, and I'll get a single space. So we will get a single space. Okay, and this space automatically is homology will be whatever homology you got in the previous case. So its homology will be the Khovanov homology, and then you still have to prove that it's a link invariant, like its stable homotopy type is unchanged under Reidemeister moves, but you still have to do the rest of it. But if you just want to construct a space, this is what you have to do. You have a cube worth of abelian groups and you want to lift it to a cube worth of spaces. Okay, So let's start, okay? And it's actually not so hard. So you fix some large k. So fix a large k. So I'll show you where we get stuck. You try to do the most obvious thing, and then you'll get stuck, okay? And then I'll try to give a hint of how to fix it. Okay, so remember what Khovanov's cube looks like. It looks like Z2, Z4, and Z2. But let me go back and actually bring you the Khovanov cube. So this is the Khovanov cube. Now this is most probably something I can do. We'll see how well it works. I should be able to copy this. On a blackboard, I'll just go to this blackboard. But here, let me just copy this. It did work. Fantastic. Okay, so this is the Khovanov cube. And now I want to lift it to the category of spaces. So what space, I mean, whose reduced homology, so this is not homology, this is reduced homology, everything is reduced, okay? So it's a reduced homology. So I want to construct a space whose reduced homology is just Z2, and the most obvious candidate is like a wedge of two spheres. So let's just take a wedge of two spheres. I mean, you could choose different ones, but let's do the most obvious one. So a space whose reduced homology is Z2 is a wedge of two spheres. And let's pick like k-dimensional spheres where k is sufficiently large. So fix large k, and we are going to use k-dimensional spheres. I want to mention this. So use SK, k-dimensional spheres. Remember, we are only going to construct a space up to stable homotopy. So we are allowing spaces up to suspension. We are allowed to suspend spaces, and we don't care too much about it. So that's why I'm like freely using SK. So here I want to take SK, wedge SK. And here I want to take 4 copies of SK, SK, wedge, SK, wedge, SK, wedge, SK. And here also I want to take 4 copies of SK. And similarly here I want to take SK, wedge, SK. Where these different sphere summands correspond to the different generators. So maybe I should mention this, that here the first sphere corresponds to the 1 generator and the second sphere corresponds to X. So this corresponds to 1, and so this corresponds to these different red generators that I've already written. Okay, so just allow me 1 tensor X, X tensor 1. This will make our life easier. So X tensor 1 and X tensor X. So these different sphere summands, so I've taken just wedge sum, and these different sphere summands correspond to these different generators. Okay, now I just have to give you maps so that they commute. Okay, and then mostly it's easy, right? Like, because here this X, like let's start with these maps. So X maps to X tensor X by 1, by the map 1. So I want to map, so I want to get a map whose on the level of homology, it's that map. It's a map that already exists. So I just should map this SK to this SK, which is X tensor X. So just this map, just map this sphere to that sphere summand by the identity map. And so if I take the identity map from a sphere to a sphere, its induced map on homology is the map 1. So that's easy. So I can do this, this. Okay. So the purple ones are the ones I am already done. So I did those guys. Okay. Let's see what are the other easy ones. Okay. So similarly, like 1 tensor 1 maps to 1. Or for that matter, 1 tensor X maps to X, and X tensor 1 also maps to X. These are all mapping by sort of degree 1 maps. So everything looks like degree 1. So things are going great. So these are all like mapping by a degree 1 map. So all I do is like I take 1 tensor 1 and I map it to 1 by an identity map. Similarly, I take this 1 tensor 1 sphere and map it to that sphere. Take this sphere and map it to that sphere by the identity map. And the other 2 guys, like these 2 guys, it's getting messy, but those 2 guys, you map it to this sphere again by identity map. Just take the 1 tensor X sphere and the X tensor 1 sphere and just map them by so basically, like anytime you see a sphere mapping to another sphere by multiplication by 1, you just can map it by identity. like nothing goes wrong. Like and like the thing is that this x tensor x, guys, like what about this guy? This x tensor x, that sphere maps to nothing. So there is an x tensor x sphere right here. It should map to nothing. So just please map that to a base point. So map that to the base point. Similarly, this x tensor x maps to nothing. So please map that to the base point. So the base point is kind of lying here. There is a base point inside this wedge sum. So take this entire sphere and just map it to the base point inside the wedge sum. So we are almost done actually. So we defined all these maps. The map that we are stuck with is actually the map like where 1 maps to 1 tensor x and x tensor 1. So we define all of this. We define this. So we define what to do, like at the level of spaces, what to do for all of them. The one we are stuck with is like how to map the like this 1 maps to 1 tensor x plus x tensor 1. Right? So at the level of space, that means I have this sphere labeled 1, and I have to map it to a sphere labeled 1 tensor x, wedge a sphere labeled x tensor 1. So I have to map a sphere to a wedge of 2 spheres, and it's a sphere mapping. So this is like a sphere mapping to a wedge of 2 spheres, and it must be degree 1 on both factors. So this is like, and it has to be degree 1 on both factors. Okay, and this requires a choice. There is no natural candidate. No natural candidate. I really want to stress this. There is no natural candidate for how to map a sphere to a wedge of 2 spheres. Like here is one way you can do it. So how can you do? So it requires choices. Let me explain one sort of choices. Like, so maybe let's take so these are these things called box maps. So let's take a box, okay, a k-dimensional box. So 0, 1 to the k, okay, and let's take 2 sub-boxes, disjoint. So take 2 sub-boxes. I don't want to shade them. Okay, take 2 sub-boxes. Now what I can do is like take any 2 sub-boxes and then disjoint. I really want to stress that. Then what you can do is like once you have that, you can like send everything outside to a point. So just map everything that's outside the 2 boxes, send this entire black thing to a point. And then, so just collapse it. So take a box, 2 sub boxes, send everything outside to a point, and that will map these 2 boxes to 2 spheres. So this gives you a map. So this is a map. This is a map from a sphere to a wedge of 2 spheres. So if I have 2 boxes and I just collapse everything outside to a point, this gives me a map from a sphere to a wedge of 2 spheres. So if I want to like choose a map from a sphere to a wedge of 2 spheres, which is degree 1 on both factors, the sort of choice that I have to make is like this, that I have to choose 2 disjoint boxes, 2 disjoint sub boxes inside a bigger box. But this space of choices actually is not contractible. So like now we are getting into serious territory. So the set of all such choices is not contractible. Like, so the space of 2 sub boxes inside a big box is not a contractible space. So it has a loop, for instance. So like pi 1 is actually z mod 2. Like, why is pi 1 z mod 2? Because I can start with these 2 sub boxes, and what I can do is like I can just switch them around. Just take them and switch them around. And that's a pi 1, that's a loop. That's a loop, and it's clearly not contractible. So if k is large, it's just going to be that z mod 2, nothing else, just that one single z mod 2. But it is not contractible. So what?
Sorry to interrupt, but is this construction the same as squeezing an equator to a point?
That's right, that's right. So the special case, like, you know, like as you have learned from doing pi 2, is that if you take thing, and this could be your equator. and you're sort of squeezing that equator to a point. So your two sub boxes could have been like this. That's your equator. So, but typically boxes are drawn like more symmetrically. So you would most probably draw
proof that bit like the proof that pi2 is abelian. You know.
It's like the proof that pi2 is abelian. That's right. So because pi2 is abelian, it's like that's right. This equator can be rotated around. But this is more like the proof that this why is pi1 z mod 2. This is kind of the proof that pi n plus 1, or maybe I'm using k plus 1, pi k plus 1 of sk is actually z mod 2. That there is like if you look at like maps from a sphere to a sphere, there's a z mod 2. That space of maps from a sphere to a sphere also has homotopy, like also is not contractible. That's z mod 2. Okay, so
you need k greater than 1. Yeah.
Which one?
You need k greater than 2.
That's right. That's right. So that's why I said k is greater than equal to, like much larger. That's right. That's right. So for instance, if I'm just like actually doing the pictures that I'm drawing, so if I am actually considering this type of pictures, here actually this space has a z, because I can take two, like in a square, I can take two subsquares and I can just like keep turning them around, and these are all non-trivial. I cannot undo that. But in a three-dimensional space, I like going around multiple times, I can just like get rid of that. Okay, because it's three-dimensional. But so if k is larger, like sufficiently large, the space of like two sub boxes inside a big box just turns out to be z mod 2. Like pi1 is z mod 2, and it has higher pi i's as well. Like there's like more fundamental groups. So we are okay with making choices. So we are actually stuck here. Like we want to send a sphere to a wedge of two spheres, which is degree 1 on both factors. And immediately we realize that this requires choices. You either like choose two sub boxes, or as Roger said, we choose an equator. Choosing an equator is also fine. But whatever you do, you are required to make choices. We are okay with making choices as long as the choices are being made from a contractible space, because then we know that we will not get stuck. But here the space is not contractible. The space has pi1 right off the bat. Okay, so I'll tell you like the way we fix it. So the fix is that, well, the space of and this time I'll go really fast, but the space of sort of labeled boxes, labeled sub boxes in 0, 1 to the k is highly connected. I mean, it's not contractible, but it's highly connected. Like it's, I think, k minus 2 connected. So it has no homotopy group up to k minus 2. So if I'm considering labeled sub boxes, like the boxes are not like just, so here is a box and here is a box, but I'm going to label it, this is A and this is B. So then I cannot just interchange the two boxes, because then I've changed the labels. So if I consider the space of labeled boxes, then it's k minus 2 connected. It's very highly connected, so it's almost contractible. So this means it's basically contractible. It's as contractible as we need it to be by increasing k. Okay, so it's as contractible as we need it to be. So, and then you realize that I could make them. So I cannot get these maps. So I want to construct this map. I really want to construct this map. Okay, so this would correspond to like choosing two sub boxes inside a big box. Let me move over. So I have this big box corresponding to S1, this guy. There's a big box, and I want to map it to S1 tensor X and S X tensor 1. So that requires choosing two sub boxes, but these boxes are actually labeled. This is like 1 tensor X and X tensor 1, because it's mapping to this sphere, wedge, that sphere. So these boxes, so if I want to choose a map from here to here, this is kind of, I am choosing labeled boxes. So in that case, it is sort of contractible. So I could define this guy. So this S1, I could map to 1 tensor X and S tensor 1 by choosing labeled sub boxes, choosing labeled sub boxes of 0, 1 to the k. So if I choose labeled subboxes of 0, 1 to the k, where these are the labels, then I can do it. Okay, but what are the labels? Okay, here is like, so the labels, it's getting a lot of tricky. What are the labels? The labels are these two labels, 1 tensor x and x tensor 1. So if I want to map this sphere to a wedge of those two spheres, I have to choose subboxes. I could label them by whatever these labels are. Okay. Similarly, I could define this guy to a wedge of those two spheres, but now the labels are sort of these guys. Those are the labels. And now these labels have nothing to do with these labels. Like, because these are labels, like, you know, if you go all the way back, these are labels of, these are these two labels, while those are these two labels. Like, these labels are labels of, so what were the two circles? If I go all the way back, yeah, so the picture looks like this. So the picture kind of, here is the cube. So these two labels, so if I'm going the top way, when I'm defining these two maps, I am choosing two boxes labeled by these guys, so which are labeling of these two circles. On the other hand, if I am going, L is black, if I am going by these boxes, I am choosing these two labels, which are the labelings of these two circles. And well, these circles, the labeling of these circles have nothing to do with the labeling of these circles, right? So I better make sure that they have the same type of labelings, and this is this extra amount of choice. So this is extra sort of data that we have to do. That, so there's like sort of, so we need some extra geometric input where we sort of choose a bijection between this type of circles and this type of circles. So we choose a bijection between the circles, like, so between the circles here. So we choose a bijection between the circles so that the labeling of these circles corresponds to the labeling of that circles. So this requires some choice, because there are two possible bijections, but we have to choose one so that the labelings of these circles correspond to the labelings of those circles. So this requires a choice. We call it a ladybug matching for some reason that I won't be able to explain. So we call it a ladybug matching. There are two choices, and we require it to be consistent. Like this has to be like this sort of choice has to make sense globally. So it's not just a local picture. This I mean, so I want to just say this. So this choice has to be in some sense consistent globally. So there's a little bit of topology that one needs to do to make sure that this choice is consistent globally. And then once you choose that, then you have sort of chosen a bijection between these two circles here and these two circles here globally. And then back to this story, that means we have got a map here where the boxes are labeled by these labels, and we have got a map here where the boxes are labeled by these labels, but the labels are actually in bijection. So this map and that map, they are both doing boxes labeled by the same labels, and that space is contractible. So you're now choosing maps from some contractible spaces, and then so things are easier. Like you won't get stuck, and you can keep going, and you'll eventually be able to construct a cube of spaces. You'll be able to eventually construct a cube of spaces which lifts this cube of abelian groups. And once you get a cube of spaces, which lifts this cube of abelian groups, you can get iterated mapping cones, and you get a single space out of it. Okay, whose homology will be Khovanov homology, and then you have to check that its stable homotopy type will also be an invariant. Okay, and then this has many applications, many generalizations, like the ones that I mentioned at the beginning. Okay, so that's like a very, very brief summary of how the construction works. So let me stop here. I am over time, sorry, but
Oh, there's no problem. No problem. No, it was a fascinating talk. So thank you very much. Can I just ask you to do one thing? Don't get rid of these notes. If you could maybe make a copy and send to Lou.
Yeah, and
Sure.
we'll put them in the Dropbox so people can look at
And
it.
also, we would be very grateful for any off prints, virtual off prints of any of your work on this.
I think so. All the works are on archive, right? I mean, everything, like except the one that about cobordism maps, which we are writing up. Okay, and I think we are almost written up. We are proofreading actually. So, but so it'll land in the archive soon. So everything else is on the archive. But these are sort of very technical. Like I really try to hide the technicality. Like this sort of things get very technical, but very fast. But there are some sort of review type things which we wrote, and so those might be better for a start.
Yeah, when you send me the notes, if you would send me your best recommendations for any review articles, that would be great. We can also put them in there.
And I can share it with you. Somebody like, okay, I can like, I'll send it after the talk. Okay, I can just share this.
Sure.
Okay, I'll send it after the talk.
A question: how does the description you gave today compare with your flow category kind of description?
So it's the farthest from the flow category description. So the description I gave today is very close to maybe it's closer, much closer to the construction by Hook-Krish. So where did I write them? So yeah, Hook-Krish. So the right around the time when we were doing constructing the space using, so first we constructed the space using flow categories. This is following Cohen-Jones-Siegel. So they have a mechanism for constructing a flow category and getting a space out of it. So we constructed a flow category, and so that was our construction, the one with Robert Lipschitz. So around the same time, Hook-Krish, they were constructing a K-theory lift of Khovanov homology. So they constructed a K-theory lift. And then, so then we realized that you can actually lift it to a space all the way if you're slightly more careful. And so this definition is, okay, so then in this joint paper with Lawson and Lipschitz, we showed that these two definitions are the same, but we actually, it took a long time. So because our definitions are very far away to start with, so we had to construct 5 sort of intermediate definitions. So this paper has 5 definitions of Khovanov homotopy type, but the definitions are sort of like mile markers, right? I mean, they're intermediate from this definition to that one. So the definition that I am giving, that I gave here is maybe, what do I want to say? It's 2/3 of the way from the flow, or maybe 4/5 of the way from the flow category and 1/5 of the way from this. Okay, so,
and which one of your papers is closest to the description that you gave today?
So yeah, so this is that will be so. I mean, this paper has, of course, all the definitions, but there's some review articles. This is, I think, the easiest one. So in all the the review type things that we wrote, we use this definition because this is sort of the least technical or the easiest to sort of parse. Yeah, so I think that'll be this one. I mean, so the review ones. I'll send you some papers. Yeah.
Great.
I have a question.
Yeah.
Is it possible to lift Khovanov theory to homotopy types on the nose rather than just stable?
I don't know actually. So this is actually, so we just make things very large. But you could ask that, what about unstable? Actually, this was a question Bill Browder used to ask me every time I met him, at Princeton. So when I was at Princeton, he was like, what about unstable? And then, I don't know. So of course there's some obvious thing, Khovanov homology has some, Khovanov homology is a homology group, but the way it's defined, I didn't tell you what the gradings are, but sometimes the gradings are supported in negative gradings. So of course I cannot get a space whose gradings are in negative, but that's not really a serious problem. You could ask that, what about the 10th suspension? Okay, so maybe you take Khovanov homology and shift grading by 10 or some number depending on the link diagram. And then, so that it now lies in positive gradings. Okay, you shift it by some number which depends only on the link diagram, and now it's in positive gradings. And you can ask, what about some unstable space, like an unstable homotopy type? Can you construct one which is, which is still an invariant?
Yeah.
And so it's a perfectly valid question to which I don't have an answer to. Okay, so yeah, that's all.
You don't know any reason that's not possible?
I don't know any reason it's not possible.
So is the action of the Frobenius algebra, is that living inside the sphere spectrum somehow?
That's not. So that's another great question. So that's yeah. So there's lots of things I don't know. So the Khovanov, like the way Khovanov TQFT is defined is like, he applies this Khovanov TQFT, and then the Khovanov TQFT is actually coming from a Frobenius algebra. This is an algebra, right? Like you're multiplying by the actual algebra multiplication, and when you are splitting, you're actually doing the co-multiplication in the Frobenius algebra. So there is a Frobenius algebra, and it has a multiplication or co-multiplication, and that's what you're doing. Okay, you are actually seeing the multiplication here and the co-multiplication here. Okay, and then so that's actually you could say it like, but when you're doing so this is like 1, that's x, this is like 1 tensor 1, this is like, so there's an action of x, right? You can multiply by x or things like that, and that just totally vanishes, because when we're doing the space, we just treat this 1 and this x as just labels of the circle. We don't like treat them as like Frobenius algebra elements. So there's a sphere and there's another sphere, and we are just taking the wedge of 2 spheres. We are sort of entirely doing combinatorics. So the quantum grading, the grading that I didn't mention, so there's a quantum grading on Khovanov homology where this 1 and this x actually live in different quantum gradings. And this one tensor, so these 4 guys actually live in 4 different quantum gradings. They all live in different quantum gradings. And the Frobenius algebra action sort of like interchanges the different gradings. It sees like some sort of a relationship between the different gradings. And our space does not. Our space, like the entire construction just splits across gradings. Like we see no relation between something happening in quantum grading 5 and something happening in quantum grading 7. So it's just like, so that shouldn't be the case. Like again, like there most probably is some, like, so we are only seeing sort of the tip of the iceberg. We should most probably get like some more interesting space which actually does see the relation between the different quantum gradings, but we don't see that. And this is actually again related to this thing that we don't know. So this Lie or the Bernoulli perturbation, these ones are actually the ones which see the relationship between the different quantum gradings. So these perturbations mix up the different quantum gradings. So that's where these perturbations come from. And we currently don't have any idea of how to like lift the spaces to these perturbations. If we could, then we will see relationship between the different quantum gradings and the different, like the Frobenius algebra action. Yeah.
Okay, thank you.
Well, any more questions? If not, I'd just like to thank Sucharit very, very much for a very interesting talk. Thank you, Sucharit.
Yeah, thanks, and thanks meeting all of you virtually. Thanks.
Yeah.
I'll second that. Thank you.
Yeah.
Yes, thanks very much.
So this will be recorded, and I'll send around it'll be on YouTube in a day or two, and I'll send around details. So, and I'll also send around next the talk for next week as well. Okay, so bye everyone.
Bye. Thanks.
Thank you very much.
Thanks a lot.